So for our project, we had to design a poorly mixed vessel, which was modeled as a well-mixed two-stage vessel with a heater at the bottom and a recycle stream in between. The first start, we began with a dynamic mass and energy balance. Using this, we were able to derive the relationships between the flow rates inside of the tanks, which were obviously set equal to each other since it's being modeled one vessel. Then we will use the energy balances to find the relationships between the temperature and the time and constants that were found inside of the vessel. This was also done for the outlet temperature as well as the bottom part of the vessel's temperature. Then we will use Laplace transforms to model the relationships between the inlet and between the outlet temperature, so that we could solve for gain and time constant values for each part of the system. This was done right here, and with this we were then able to model the entire process inside of a block diagram. This block diagram has the set point temperature controlling the outlet temperature with a disturbance variable from the inlet temperature. This was then represented in its final form to show a relationship between the inlet and outlet temperatures in order to condense this down into a more definitive block diagram, which can be seen right there. And using this, we then solve for more gain values as a relationship between the set point temperature and the temperature that was on the outlet. Then we included our control system into the process, which helped to solve for the overall block diagram. Using this, using all this information, we were then able to solve for the valve constants, the time gain between the time constant and the gain from the valve, using data that was given to us in class, and this was done in an Excel file with the temperature from the steam at the bottom of the vessel being the controlling aspect for finding that. Following this, we then analyzed the exit temperature with a test set of variables, and this was very important for solving for the relationships inside of the reactor and the temperature that would then be fit to the outlet temperature model inside of the reactor. We did this by using relationships found between the outlet temperature, and in doing this, we were then able to use a Heaviside expansion to use the form of this equation. And with that Heaviside, we had a first order alpha constant that was solved for, and then two second order alphas that were then solved for as well, that were all in terms of the zeta value, the gain values, and the time constant within the valve, which were all responses or variables that were going to affect the outlet temperature. With this, we were then able to Laplace transform the entire equation using the Heaviside expansion that we had done previously. And with the Heaviside expansion, we were able to find this relationship between the temperature and the time. And this data was then fit to a model in Excel using this equation, alongside the constants that were found inside of the previous parts of the setup. Along with this, we then set the energy balance equation solve the energy balance using a steady state equation. The steady state equation for the temperature on the second reactor. This was done by setting the energy balance on the second vessel equal to 0. Once we did this, we then could solve for the UA in terms of the flow rates that were coming inside and outside of the reactor. as well as other design variables that were solved for previously. This relationship also allowed us to solve for the steady state temperature that should be fed in at the second volumes space, and this would change later on whenever we did not use the test values anymore. In order to find a minimum flow rate inside of the reactor so that we could use that as a baseline for the Excel data analysis, we solved for a Qmin equation, or solved for Qmin with this equation, and this was used for helping to analyze further parts of the process. Along with this, we were able to show that the zeta value inside of our process would be greater than 1 at all times, giving an overdamped response. And with this, all of our information, as I said previously, we then plugged all of the equations from the previous steps into into the Excel document, so that we could use Solver and solve for the expected flow rate that would be used, as well as the volume that should be used inside of the reactor. This was all based off of test data, and would be later changed to fit other design conditions, which we see here. This was done by extrapolating the previous found values from the test data, such as QR, V1, V2, or UA. And with this, we were able to solve for new time constants, as well as new gains, and a new, as I mentioned previously, steady state temperature for the set point, as well as the temperature in the bottom of the vessel due to the heater. With all of this information, we were then well on our way to designing this reactor, this process inside of for our PI controller. And in order to finalize these values, we had to do a controller tuning, which was important for finding the ultimate gain and the time constant that would be associated with this. This is very important for understanding the accuracy of the model, as well as the ability for the model to respond quickly to different variables or changes inside of the vessel. This was done by solving for a characteristic equation that was modeled with the gains as well as the open loop Laplace transform that would be then set equal to 0. Once we had this, we could solve for the omega value, which was used by plugging in our known variables, and then with our direct substitution, we could then separate into real and imaginary parts and find our omega value. The omega value is also very important because it is basically the amount of frequency or the oscillatory response that is going to be felt whenever we change add an input or change the set point so that we can have a response. Once we've found these values, we were now ready to model our entire system inside of Simulink. Now, the Simulink model that I have for my executive summary is lacking oscillatory motion. I think this is due to the zeta value that I have found for my system, which would be in my Excel document can be found, but it is like around 3.4. And with this zeta value, we are going to see an overdamped response, which does not give us oscillatory motion. And the maximum amount of temperature differential that was seen from my temperature change inside of the process was 10 degrees Celsius. Thank you.